Every bridge on Earth, from a plank over a stream to a 2-kilometer span across the sea, is really just a solution to one single problem. How do you hold something up across a gap where there is nothing underneath to hold it? There are only a handful of genuinely different answers to that question, and once you can see them, you will never look at a bridge the same way again. Before any of the bridge types make sense, you need just two words, and they explain the entire subject. Compression and tension. Compression is squeezing, pushing a material together. Tension is stretching, pulling it apart. Every part of every bridge is doing one of those two things at any moment, and the whole art of bridge design is steering the forces from the traffic on top, through the structure, and safely down into the ground, while making sure nothing is squeezed or stretched harder than the material can bear. Different materials have very different feelings about this. Stone and concrete are brilliant in compression and hopeless in tension. They will carry a mountain if you push straight down, but pull on them and they crack. Steel and cable are the opposite, superb in tension, happy to be stretched to enormous loads. Almost every bridge is, at heart, a clever arrangement to make sure each material only ever gets the kind of force it is good at. The simplest bridge in the world is the beam, a single rigid deck laid across two supports. You have built one every time you have dropped a plank across a ditch. When a load sits on the middle of a beam, something subtle and important happens inside it. The beam tries to sag, and as it does, the top surface gets squeezed together in compression, while the bottom surface gets stretched apart in tension. That is why a steel beam for a bridge is not a solid rectangle but an I shape, with most of the metal concentrated in a flange along the top and the bottom, exactly where the squeezing and stretching are fiercest, and a thin web in the middle where little is happening. The beam is cheap, simple, and everywhere, carrying the vast majority of the world's ordinary road and rail bridges. But it has a hard limit. The longer you make a beam, the more it sags under its own weight, until eventually it is spending all its strength just holding itself up. That is why beam bridges are short, and why the long crossings need something clever, a way to get rid of that tension the beam struggles with. The oldest clever answer is the arch, and it is a beautiful piece of physics. An arch is a curve of material that turns the downward push of a load into compression, running all the way around the curve, squeezing each block against its neighbors, and delivering the force down and outwards into the supports at each end, called the abutments. The genius of this is that the entire structure is in compression, with almost no tension anywhere. And that is exactly why the Romans could build arches out of stone and concrete, materials that are useless in tension, and why so many of those arches are still standing 2,000 years later. An arch pushes outward at the bottom as well as down, so it needs solid rock or heavy abutments to push back against, or it will spread and collapse. Build an arch well though, and it is astonishingly strong and astonishingly durable, using less material than a beam for the same span. Modern arches in steel and concrete stretch far longer than any stone one ever could, but they are all doing the identical thing the Roman ones did, turning load into pure compression. Look at an old railway bridge or a metal footbridge, and you will see a lattice of triangles, and that is a truss. The triangle is the key, because it is the one shape that cannot be pushed out of square without actually changing the length of its sides, which makes it rigid where a rectangle would simply fold over. By building a bridge out of a web of triangles, engineers create a structure that is both stiff and light, because every individual bar in the truss is arranged to be doing only one clean job, either pure compression or pure tension, never bending. As a load rolls across, the top bars are generally squeezed in compression, the bottom bars are stretched in tension, and the diagonals carry the load out to the supports. Because each member is a simple strut or tie, you can use surprisingly little material to carry a very large load across a respectable span. Trusses were the workhorse of the great age of the railways, and the same triangular logic holds up cranes, pylons, and the roofs over enormous halls. Between the truss and the giant spans sits a method that solved a very practical problem: how to build out over a gap too wide to prop up from below, and too deep or too busy to fill with scaffolding. The answer is the cantilever. A cantilever is any beam that is anchored solidly at one end and reaches out unsupported into thin air at the other, like a diving board. In a cantilever bridge, engineers build two of these arms out from two piers, each one balanced and held down at its anchored end, reaching towards the middle of the gap from opposite sides. Because each arm is firmly rooted at the pier, it can extend a long way without anything underneath it, and the two arms either meet in the center or carry a short suspended span dropped between their tips. The beauty of it is in the construction, because the bridge supports itself at every stage of being built, growing out over the water without ever needing falsework rising from the riverbed below. The great steel cantilevers of the railway age, like the mighty Forth Bridge in Scotland, work exactly this way. And if you look at one, you can read the forces straight off its shape, the top members stretched in tension, the bottom members squeezed in compression, all of it balanced around the piers. For the truly enormous gaps, the ones measured in kilometers, everything flips around and the structure hangs from above rather than standing from below. This is the suspension bridge, and it is the purest expression of using tension. Two tall towers carry a pair of massive main cables that sweep in a graceful curve from one end of the bridge to the other. The entire weight of the deck, and every vehicle on it, hangs from those main cables on hundreds of thin vertical hangers, so the deck is held up by tension, all along its length. That load runs along the main cables as tension, is delivered to the tops of the two towers, which carry it straight down as compression into deep foundations. And the enormous pull left over at the ends is taken by gigantic concrete anchorages buried in the ground, holding the cable ends like the pegs of a tent. Because a steel cable in tension is so phenomenally efficient, this is the only arrangement that can cross the very longest spans. The longest suspension bridges reach nearly 2 kilometers in a single leap, distances no beam, arch, or truss could ever dream of. There is one more you see constantly on modern crossings, and people often mistake it for a suspension bridge, but it works differently, and understanding the difference is the final piece. This is the cable-stayed bridge, the one where straight cables fan directly out from a tall central tower down to the deck, often in a striking harp or fan pattern. Here there is no huge draped main cable and usually no massive anchorage. Instead, each stay cable runs in a straight line from the deck up to the tower, holding its piece of the deck in tension and passing that load directly down the tower as compression into the foundation. The tower does almost all the work, which is why cable-stayed bridges have those dramatic single pylons. They are quicker and cheaper to build than a full suspension bridge because they need no giant anchorages, and they are ideal for the middle range of spans, longer than a sensible arch or truss, but shorter than the monster suspension crossings. That is why almost every big new bridge built this century, spanning a river or a motorway, is a cable-stayed one. There is a part of every bridge that almost nobody thinks about, because most of it is invisible, and yet it is where bridges are most often won or lost. The foundations. A bridge does not just have to hold up its deck, it has to deliver every one of those forces. The compression from the towers, the outward thrust of the arches, the enormous pull of the anchorages, down into ground that is often soft riverbed or the bottom of the sea. For a bridge pier standing in water, engineers frequently build inside a cofferdam, a temporary watertight wall driven into the riverbed and pumped dry, so crews can excavate and pour concrete on what is briefly dry land in the middle of the river. Where the good rock lies deep, they sink caissons, giant hollow boxes that are lowered to the bottom and dug out from within, gradually descending until they reach ground solid enough to carry the load, and then filled with concrete to become the foundation itself. The towers of the longest suspension bridges rest on foundations the size of buildings, buried far below the waterline. It is unglamorous, hidden work, but a bridge is only ever as trustworthy as the ground it manages to stand on, and the deeper the water and the softer the bed, the more of the real engineering is spent down there, out of sight, long before the elegant span above ever takes shape. A finished bridge looks like a fixed, permanent thing, but it is quietly moving all the time, and designing for that movement is one of the subtlest parts of the whole craft. Steel and concrete expand when they are warm and shrink when they are cold, and a long steel bridge can change in length by an appreciable amount between a freezing night and a baking afternoon. If the structure were locked rigidly to the ground at both ends, that expansion would build up unimaginable forces and tear it apart, so bridges are deliberately built to move. That is what those ribbed metal expansion joints in the road surface are for. The ones your tires thrum over at each end of a span, they are gaps engineered to open and close as the bridge breathes with the temperature. The deck sits on bearings that let it slide and rotate a little, rather than being pinned solid. Add to that the constant flexing under traffic, the sway in the wind, and the slow fatigue of millions of loading cycles over decades, and you see why a bridge is never simply finished and forgotten. The great ones are inspected constantly, repainted endlessly to keep rust at bay, and fitted with sensors watching for the tiny changes that betray a problem long before it becomes dangerous. A bridge is less a static object than a machine, endlessly adjusting to heat, load, and wind, and holding itself together while it does. So which bridge gets built comes down mostly to one thing: the length of the gap, and after that the ground, the budget, and what has to pass underneath. A short country crossing gets a beam. A rocky gorge with solid walls invites an arch. A medium river crossing today usually gets cable-stayed, and only the truly vast gaps, the mouths of bays and straits, justify the enormous cost of a suspension bridge. But length is not the only enemy. For the big lightweight spans, the real danger is not weight at all, it is wind. A long, thin deck hanging in the air can catch the wind and begin to twist and oscillate. And if the rhythm of the wind matches the natural sway of the bridge, those movements can build on themselves until the bridge tears itself apart, which is exactly what happened to the Tacoma Narrows bridge in 1940, famously twisting itself to destruction in a moderate wind. Ever since, engineers test big bridge designs in wind tunnels and shape the decks like aircraft wings to let the air slip past cleanly. So the very bridges that span the widest gaps are also the ones most carefully designed to make friends with the wind. And that is really the whole story of bridges: beam, arch, truss, suspension, and cable stayed. 5 ways of answering the same ancient question of how to cross a gap with nothing underneath. Each one is simply a different route for steering compression and tension from the traffic down into the ground, each suited to a different length and a different landscape, each letting stone, steel, and cable do only the job it is best at. The next time you drive across a bridge, look at its shape for a second. Whether it is a simple beam, a curving arch, a web of triangles, a great draped cable, or a fan of straight stays, and you will know just from the shape exactly how the forces are moving beneath your wheels, and how that structure is quietly holding you up over the emptiness below. Follow for more construction facts hiding in plain sight.